topic for today's class is multi-class classifications using multi-layered perceptrons. So, too many classes and too many multis in our title. Anyway, before we begin the actual topic of the day, let us go back to what we were discussing in the last class. We were basically discussing some of the heuristics that would help in making the backpropagation or multilayered perceptron networks perform better. And in that we had already listed out 5 or 6 factors, okay, which affect the performance of the multilayered perceptrons, and there are a couple of heuristics which we need to cover further. Okay. They are quite simple enough, so it will take, I mean, the first few minutes of today's class I will be taking in order to explain the remaining heuristics which are used for the performance improvement of the multilayered perceptrons. So, we have listed up to 6 heuristics so far, and the 7th one that we need to talk about is the learning from hints. In fact, what we mean by this is that when we are actually training a neural network, what we are doing is that we are providing the information pertaining to the input output pairs. So, we have got a set of inputs, okay, in the form of vectors, okay, and their corresponding outputs, okay. So, this input output pairs that we are feeding effectively is helping us in determining the unknown input output mapping function. Okay. After all, what we are going to find out is the unknown function which describes the particular input output relationship. Now, we do not feed any mathematical equation to those functions, but from the examples we derive that what kind of function it is, okay, from the examples that the neural network is made to learn. Okay. Now, although typically a neural network can approximate a function, and in fact we had seen the functional approximation in the case of single layer perceptrons earlier, but anyway such kind of functional approximations can also be generalized for the case of multilayered perceptrons. But the thing is that in order to expedite the learning process, it will be better, in order to expedite the process and also make the performance better, okay, it is always good if we can impart some a priori knowledge. So, what we are looking for is some a priori knowledge about the function. Okay. We may not know the exact mathematical relationship describing the function, but we may be referring to some properties pertaining to the function. We may be having a priori idea about that. Properties in the sense, let us say symmetries. Okay. Supposing we know that a function is odd symmetric about the point 0, okay, or it is even symmetric, or if the function is invariant with respect to some of the parameters. So, symmetries, invariance, okay, like that several such a priori ideas, okay, can be imparted into the training process, okay, so as to make the performance better. And this is exactly what we mean by learning from hints. It is as if to say that when a question is asked which one finds difficulty in answering, one does not have the exact solution of that, okay, then a lot of times we provide some hints to that problem, okay, that how exactly I mean, one can attempt to solve this problem. So, it is, I mean, from, I mean by that same notion that the word hints is used, okay, where some amount of a priori knowledge is imparted into the process. And the eighth and the last heuristics which we are going to consider is the aspect of learning rates. Okay. Now, we have been assuming so far, I mean that is more for the simplicity, that for a multi-layered perceptrons, okay, its learning rule that we had used earlier, I mean you will be remembering that all the time we are having a factor eta which is the learning rate, and the very fact that we are using eta without giving any further suffixes to it means that as if the eta is going to remain constant throughout the iterations, and also for the I mean since it is a multi-layered perceptron and essentially it is structured into several layers. I mean it is having the input layer and one or more number of hidden layers, and finally it is followed by an output layer. When so many layers are existing, then also the inherent assumption by taking a constant learning rate eta is that the learning rate is the same for the synaptic weight updatings, no matter whether it is output to the last hidden layer or hidden layer 2 to hidden layer 1, like that. Okay. We are assuming that the learning rate is same throughout, but really speaking, should it be same? Okay. I mean for the purpose of simplicity we may say that okay, that simplifies our task because we do not have to handle too many etas at the same time, we do not have to fine tune so many different parameters, I mean if the eta is made variable. But the thing that we should note is that when we are making a neural network learn, when we are making a multi-layer perceptron learn, okay, how are we doing that? We are finding out that what is the error that is existing at the output layer. I mean at the output neurons we are having the expected values of the output, that is to say the targets are available at the outputs. Okay. We are also computing the outputs based on the weights which are synaptic weights which are existing in the network right now, and then we are finding out the error, and based on that error, okay, we are updating the weights. In fact, the error that we are having, okay, now I mean in fact the weights are updated in accordance with their local gradients, and local gradients is definitely dependent upon the errors, and the local gradients in fact happens to be of, I mean what would you expect? Would you expect the local gradient to be higher in the layers that are closer to the output or higher in the layers which are closer to the input? I mean any guess that you should I mean that you are in a position to apply? Closer to the output you will have more gradients, yes, in fact that is so, because what happens is that we are finding the output, I mean the error, I mean the first error that we are computing is at the output itself, okay, I mean at the output layer itself, and then we are propagating those errors, okay, backwards. In fact, while propagating, it is seen that the contributions of those error terms from the previous layers, that is less, because the errors are actually contributed from all the neurons that is feeding to the output layer. Okay. So, that is why the individual contributions of the hidden layer which is previous to the output will be expected to be less than that of the output, and likewise as we go backwards the local gradient is expected to be less. So, if the local gradients are less as we proceed from the output to the input, okay, then it makes sense in having what, higher etas closer to the outputs or lower etas. If the local gradient is more, I mean as it is for I mean for the layers closer to the output, okay, there we should have, because of high local gradients, we should use smaller etas. So, we should use small eta values, okay, in the later layers. By later layers I mean ones that are closer to the output, okay, as so we can say smaller eta values in the later layers as compared to the earlier layers. By earlier layers I mean to say the layers which are closer to the input. So, we are not really I mean if we want the multilayered perceptron to work well, we are not going to keep eta as a constant. Eta can be made to vary according to the layer, and we should have smaller eta values in the later layers, and we should have larger eta values in the earlier layers, so that actually the more difficulty in learning will be for the earlier layers. So, in order to ensure that the network uniformly learns, okay, at the layers closer to the input as well as the layers closer to the output, okay, we should have the eta distribution like this, smaller in the later layers and larger in the earlier layers, right. So, that is the heuristics point number 8. So, I mean now that all these heuristics are covered, okay, we can go into the next topic, which is the multi-class classification, but I can just give a brief pause, okay, if you have any questions pertaining to the heuristic aspects that we have discussed.
How do you vary eta in this case?
How do we vary eta in this case? Well, I mean again, I mean it's very difficult to give any explicit answer to that, okay. We, I mean while designing the learning, okay, we have to just use smaller etas in the later and larger in the earlier, okay, and it again I mean the choice of that should be heuristically determined, okay. I mean if we have some heuristics, we can be dictated by that, otherwise we can simply follow some definite rule that as you go to the I mean earlier layers, I mean increase in some manner, either linearly, non-linearly, whatever. So, I think it is very difficult to give any definite answer to this, that how exactly one varies this eta, okay. It is more or less like a free choice. But the thing is that yes, I mean rather than using uniform eta everywhere, okay, you or to say, I mean one can go by the experience that if it is seen that I mean by the initial choice of the etas that we are having is definitely not uniformly learning throughout. I mean it is not uniformly having a good learn for the input layers as well as for the layers closer to the outputs. In that case, we can think of modifying the eta distribution, okay.
For neurons in the same layer.
For a?
Neurons in the same layer.
Yeah. For the neurons in the same layer, we keep the same eta. We keep the same eta there, yes.
For the same thing for the hints, how do we physically incorporate a hint into the perceptron? I mean, do we update the weight or do we change the?
Yeah, I mean in fact yes, what happens is that yes, the question is that how do we import the hints. Yes, again that is also a very interesting question. In fact, what we can do is that, I mean if we are knowing about such kind of properties, symmetries and invariances, okay, then in the training itself it is possible for us to generate some extra training sets. I mean they may not be from the exact experience, but if it is known that the function is symmetric or antisymmetric, okay, you can create the extra examples out of that, and or you can use the function properties in whatever ways you can think of. So, these are the heuristic points that one should keep in mind, and now we would like to go over to the, oh yes please.
We discussed about normalization of inputs as one of the heuristics.
Normalization of inputs as one of the heuristics, yes.
So, when we are normalizing the input, do we need in the for the training pattern, do we need to make a corresponding change to the desired outputs at the same time on the similar mathematical transformation has to be done for the desired outputs also?
Yes, yes, yes. Mathematical transformations need to be done there. Yes, sure. So, this is about the topic of the day, multi-class classifications using multi-layered perceptrons. Now, here what we are fundamentally going to consider is that we are considering a network which has got the capability to generate multiple classes. In fact, we did a classification problem in the singular perceptrons also, and just for our oversimplicity's sake, we used to take it as a two-class classifier problems. A perceptron that could classify it into either the class C1 or into the class C2. Okay, that's what we had discussed. And now that we have got a multi-layered perceptrons, okay, we can think of perceptrons having multiple number of outputs. So, we have got a multi-layered perceptron network over here. And this multilayered perceptron will be described by its weight vector. So, the W vector that we are writing is the synaptic weight vector for that, and we will be having to this multilayered perceptron the inputs, and we are assuming m dimensional inputs as before. Okay. So, there are m dimensional inputs, and we can assume that there are capital N as the number of patterns, right. So, let us take any pattern, let us take the jth pattern. So, we can denote the jth pattern by x of j. In fact, we are going to write it as the x vector suffix j, okay, because all the x's, that is the inputs, are going to be vectors since they are in the m dimensional space. And the multilayered perceptron is going to generate outputs, and in fact, it is a multi-class classification problem. So, we should have multiple number of outputs. So, let us say that we are considering an m class classifier, okay, meaning that there are m number of classes. So, if there are m number of classes, then we should have m number of outputs there. So, we can denote the output as number 1, 2, etc. up to m over here. Okay. In fact, the outputs that we are generating will be indicated by y. So, we should have, we should be writing it as y 1 comma j. Okay, the first one we should be writing as 1 comma j, and why comma j? Because that is the output of 1 in response to the pattern x of j. Okay. So, there are n number of patterns, and out of that we have picked up the jth pattern, and y1 comma j is the output of the neuron 1 at the output layer in response to the pattern x of j. And likewise, this will be written as y2j, the last one will be written as ymj. Okay. So, these are the outputs, and there are in effect m distinct classes. That means to say that the inputs that we are having, the inputs are in fact going to be points in the small m dimensional space. Okay. So, effectively if we imagine an m dimensional space, all these inputs will be having some discrete points, and now each of these points will be indicating one pattern. Okay. Now, each of these patterns will be belonging to some class, one of those m classes, and if we make an union of all the m classes. So, if we make an union of all the m classes, then it leads to the input space, the entire input space. Okay. So, union of m classes forms the entire input space. Okay. Now, what happens that there are m number of outputs, but definitely x of j is one pattern. So, x of j will belong to any one out of these m classes. I mean, it cannot belong to more than one classes. Certainly, in that case, it is an ambiguous classification. If for a particular pattern we declare that there are two possible classes, okay, that is not the unambiguous answer that we are giving. We are giving ambiguous answers if we have multiple number of classes for the same input. So, definitely for unambiguous classification, which is our aim, only one of the classes should be active and all the other classes should be inactive. I mean, all the other classes should not be there. In fact, we can simply look at the classification problem, okay, in the easiest way, that we can imagine that all these y's that we are generating as outputs, okay, are all binaries. Binaries indicating that when the outputs are 0, that means to say that it does not, I mean, the pattern x of j, I mean, if the output k or if y k j is equal to 0, this will mean that the pattern x of j does not belong to the class k, okay. And if we have y k j equal to 1, that means to say that the pattern j belongs to the class k, okay. So, we can imagine like a binary, or other possibility is that if we do not have, I mean, because the problem is of what nature we do not know. If it is not exactly like a binary, because after all we will be using the activation functions like the logistic function or tan hyperbolic, we will be using any sigmoidal functions which are essentially continuous functions. So, it can have values in between 0 and 1 as well, in which case, okay, the classification has to be looked upon based on some membership function. Like if we feed a pattern x of j to the input of the system and observe that what are the outputs, what the outputs are, then it may be that we find, I mean, supposing we find that one of the outputs is, let us say, 0.8 or 0.9, something of that nature, whereas all the other classes are indicating membership values of 0.1, 0.2 of that type. In that case, there is every reason to believe that the one which is giving us a much higher score is the correct class for that particular pattern. So, it is not mandatory that it has to be a binary, we can take real numbers also, but then the point is that the question that we have to answer is that if we have a multilayer perceptron that can classify m classes, okay, then what is the optimal number of, what is the optimal decision boundary that we can find for such kind of a classifier? That is the question that we are going to, I mean, we are trying to answer, okay, in today's class. So, now we are feeding x of j as the input and we are getting such m outputs, okay, as the classifier output. So, now let us take the kth output of such classifier. So, let ykj, okay, be the, so let ykj be the kth output of the network produced in response to x of j, right. So, that we can write ykj equal to f of xj, where f is the function. In fact, we are going to write it as Fk of xj, okay, where Fk is the mapping function that is associated with the kth output neuron, right. So, we are writing it as x of Ykj is equal to Fk of xj, okay. Now, where in this case Fk defines the mapping from input to the kth output, right. So, now we are feeding the pattern x of j and we should be getting m such responses, okay. We should be getting m such responses. So, in our case k will be varying from 1 to up to m, so that we can form an output vector, okay. So far we were writing Ykj is a scalar quantity that we were writing because we were only considering the kth output, but when we consider all these outputs together, okay, then we have to indicate it with a vector representation. So, we define a vector y of j whose components are y1 comma j the first output, y2 comma j the second output, up to ym comma j the mth or the last output. And because we are writing it like this, okay, if the original definition is a column vector, we should write it this one as a transpose of this. So, now what is y1j? y1j is f1 xj, right. So, this is the first representation. So, this is the f1 is the mapping from the input to the first output, and likewise mapping from input to the second output is going to be f2 xj, and the last mapping will be fm xj, okay. So, in fact, what we are having is I mean a vector of functions, you see. If this f1 is a mapping function, f2 is another mapping function, fm is another mapping function. So, like that we have got m different mapping functions associated with m different outputs. So, these mapping functions, so we have got a vector of the mapping functions. So, in a combined way we can write the function itself with a vector notation. So, this is one and the same as writing f vector of xj, f vector of xj vector, which means to say what? That I mean the definition of this f vector xj is that where it has got m different such elements associated with it, f1 xj, f2 xj up to fm xj. So, this is the vector valued function. So, oh yeah, is it all right? Okay. So, now here f, this is a vector valued function. So, now the question that we are trying to answer is that after an MLP, after an multilayered perceptron is trained, what should be the optimum decision rule? Decision rule means decision rule for classification. So, we can write that. So, let us see if we can answer to this question. Now, this f, which is a vector valued function, okay, it is definitely a continuous function, because after all what we are trying to do is that now I mean just like the way we have defined an output vector, okay, there will be a desired response vector also. Is it correct? Because we are having m different outputs. So, for each of these m outputs, we should expect something at the output. So, there should be an expected output of that. So, we should have a dj vector, okay, that describes the decision or the target vector. Okay. So, dj is the target vector in response to xj. Can be, cannot be. I mean, we are only making a mathematical basis for this. Okay. Later on we can always choose. I mean, for the simplest type of case, yes, if it is a clear classification problem, then definitely we should have dj to be the binary values. Okay. Even though yj's may not be binary, because yj's will be dependent upon the activation functions that we choose, dj's could be binary, because after all at the end we are looking for a crisp classification, a definite classification where we do not want any ambiguity to be there. Okay. If for some reason we want some kind of fuzziness to be incorporated in the system itself and we define a membership function, yes, in that case we can consider that even for dj we can have some kind of deviation from this 1 and 0. In fact, another thing that should be looked forward is that I think we mentioned about that point while talking about the heuristics, that if you are feeding 0 and 1 as the expected outputs, okay, in that case your region of operation is close to the saturation part of the curve, okay, where the weight adjustment is difficult, and in fact, I mean, there is a risk that it may get stuck up. So, that is why we were referring to that if it is close to 1, then you take 1 minus epsilon, and if it is close to 0, then you take 0 plus epsilon, okay, just to avoid keeping the exact 1 and the 0 values, because sometimes computationally this 1 and 0s could lead to problems. So, anyway, I mean, whether we take the exact 0 and 1 or we take some perturbed zeros and 1s, okay, that is a matter of choice that we can talk about, I mean, that we can work out later on. But yes, we need a target vector, that is definite, okay, and we are deriving the, I mean, we are just presenting the mathematical formulation of the problem. Now, f is definitely a continuous function, this vector valued function that we are talking of, it is a continuous value, I mean, it is a continuous function, and in fact, it should, what this function should look for is to minimize the risk factor. And what is the risk factor that is associated? Simply the reduction or simply the minimization of the mean square error. And how do we define the mean square error? So, we can talk about the empirical risk functional as 1 upon 2n. In fact, it should have been 1 upon n, but again because all the time we are expressing the errors as half of the error squares, okay, for the reasons that we already know. So, that is why this 1 upon 2n, but then we are having n as the number of patterns, n as the number of distinct patterns with which we are going to train. So, then we have summation j equal to 1 to n, and the minimization of the risk functional is the norm of this vector dj minus fxj, okay. And what is fxj? This fxj is nothing but it is the vector of all the outputs, that is to say k is equal to 1 to m. So, this is an m dimensional vector and this is also an m dimensional vector, and we are taking the squared norm of this. So, this is definitely the squared norm of this error that we are computing, and this is for one j, and then it has to be summed up. This squared norm is to be summed up for all the j's, that means to say all the training patterns. So, this is the risk functional that we are going to minimize. So, this is what we intend to minimize. All right. Now, yes, I mean supposing that the network is trained with binary values, as one of you were already suggesting. In fact, most of the cases it will be that. So, if we train it with binary values, then we should definitely have dkj equal to 1 when xj belongs to the class Ck, right, and it will be equal to 0 in the other case, that is when it does not belong, when xj does not belong to the class Ck. And why class Ck? Because we are considering the kth classification, and that is why we are taking dkg. Okay. So, the kth classifier will be having this kind of a distinct thing, so that actually the Ck or the class output, okay, is represented by m dimensional target vector. So, Ck basically is represented by, I mean with this kind of a binary target values. So, here we are having binary target values, and for binary target values Ck is represented by an m dimensional target vector. So, where the target vector will be 0 0 0 0 like that, and if this is the kth element, okay, the kth element of this, I mean if it belongs to Ck, okay. So, since it belongs to the class Ck, the kth element will be 1 and all other elements starting from k equal to 1 up to k equal to m is going to be 0. So, this is the m dimensional target vector. Okay. This is dj, yes, this is dj, right. Okay. So, Ck is the class. So, Ck is a class, okay. So, it is a class pertaining to the pattern x of j, simply that, okay. So, we have got m number of elements into it, because it could be in one of the m classes, and only at the right kind of class we are going to put it as 1 and all other elements are going to be zeros. Understood? No confusions? Okay. Now, one thing is there, that if we do like this, that means to say what? That we are after all going to feed a large number of such patterns, isn't it? I mean we had x of j as one instance of the input, and like that there will be several inputs that we are feeding, and for each of these inputs we are going to specify, I mean during the training, for each one of these inputs we are going to specify that what is the correct class of that. Okay. So, ultimately when our training is completed with all examples fed in, when we have fed all the examples, then we have inherently made a class probability, we have incorporated a class probability, is that correct? What I mean by that is that you have fed n number of such patterns, okay, or rather to say n number of distinct points in the small m dimensional space you have got. Now, once you have specified that to what class each of those points belong, okay, then at the end of feeding that you are getting a class probabilities which will be associated with it, right. So, that class probability we are going to call as, in statistical parlance, we are going to call it as a posteriori probabilities, okay. A posteriori probability, okay. I mean, are you familiar with this term? Yes or no? Yes. I mean, you are knowing what a priori is. A priori means that before feeding it only you know it, okay. I mean, you are starting with the knowledge, whereas a posteriori means that after getting the data you know what it is. So, it is a posteriori probability computation that leads to. So, the multi-layered perceptron that we are using for the multi-class classification problem, okay, ultimately it should lead to some asymptotic approximation of the a posteriori class probabilities. I mean, as you train it more and more, I mean, with all these m different classes, data belonging to all these m different classes, then where is it going to converge? It is going to converge into the a posteriori probability of classifications. So, if we have, let us say, a finite set of independently, identically independently distributed inputs, that is to say, if we consider IID examples, okay, this leads to an asymptotic approximation of the underlying a posteriori class probabilities. It is going to happen, okay. That is, it definitely leads to this asymptotic approximation of a posteriori class probabilities, but it is going to happen provided you fulfill two conditions, okay, and the conditions of that is that the size of the training set is large enough, so the conditions, we are stating the conditions for that. Size of the training set is large enough, and the other assumption is that the back propagation algorithm does not get stuck at local minimum. So, if these two conditions are fulfilled, in that case ultimately we are going to have, I mean, whatever a posteriori classification probabilities we have got out of these training examples, okay, it is going to lead to an asymptotic approximation of that. Okay. So, but we were in fact trying to know that which is the optimal decision rule, okay. And in order to determine this optimum output decision rule, okay, one of the output decision rules that we can simply frame is the Bayes rule, okay. So, one of the output decision rules, so the output decision rules if we apply the Bayesian rule, okay, then that says that classify x of j, okay, or any vector x, okay, as belonging to Ck, as belonging to the class Ck. So, we have got classes C1, C2 up to Cm. Okay. So, classify it into Ck if Fk of x, okay, is greater than Fj of x, okay, for all j not equal to k, right, okay, where in fact if kx and if jx, okay, are the elements of what? The f vector, elements of f vector x vector. So, what is that? I mean basically we can just express f vector x vector as the vector f1 x vector, f2 x vector up to fm x vector. Okay. So, what Bayes rule says is very simple, that you simply examine that which is the highest output value, but basically that starts with the assumption that there is a unique maximum value that is existing. Okay. There is only one winner, that is what you are assuming, but if there are multiple number of winners, if there is a tie, okay, then what is going to be your tie breaking rule? So, that is not very clearly defined from Bayes rules. Okay. Now, Bayes rule in fact will work best, okay, if the I mean if we have only one of the, I mean if it belongs to, if it really belongs to the class K, if it really belongs to the class Ck, then if we have Fk of x vector equal to 1 and all the others are zeros, all the other Fj x vectors are zeros, that means to say that the output is absolutely distinct, okay, and unambiguous. In that case, applying Bayesian rule makes some sense. But if we have, I mean if we do not have that, if we do not have such kind of binary outputs, in that case, I mean there is a risk of getting a tie. I mean the only risk of not getting a tie is that if it is absolutely binary, where there is only one output and all other 0 outputs, no tie, no ambiguity. But if the moment we allow the values other than 0 and 1, okay, you can have a tie there, and there the Bayesian rule may not be all the time applicable. And in such cases, definitely we have to go in for a different approach. Okay. And what are the other approaches that one can take? One can think of keeping some threshold. Let us say that we decide upon a threshold that if the Fj x vector is above that threshold, then we classify it into some membership. Okay. That means to say that we consider that this could be one of the probable classes, and if it is less than that threshold, then we threshold it out, meaning that we do not consider it belonging to the classes. But the latter obviously leads to multiple class assignments. In fact, I mean that is a tie case, I mean which can easily arise out of that. So, I mean whatever way we can think of, you will feel that the Bayesian rule is still the best. I mean even if we have the outputs not exactly in the binary, then also it is a good thing to apply this. But if they are, I mean still ambiguous, and we cannot have even, if we cannot even impart a priori idea about to which exact class it is going to belong, well then you toss a coin, you either put it into this class or the other class. But the output decision making function, okay, can also be described in an alternative way. You see that if somebody asks us to talk about the decision surface or the decision boundary, okay, then that decision boundary can be modeled in terms of the networks, in terms of its hidden layer also. So, the decision boundary, so when we have, in fact, let me explain it in a more clearer term, okay, that when the decision boundary is formed by the thresholds that I was explaining, is formed by thresholding the outputs against some fixed values, then the overall size, overall shape and orientation of the decision boundary may be heuristically expressed in terms of its hidden number of hidden neurons and in terms of the ratios of synaptic weights. Okay, followed what I mean, that when you use such kind of a thresholding schemes, okay, then it is a question of just expressing the decision boundary, okay, where instead of expressing the decision boundary as a simple Bayesian rule, you can express it in terms of the number of hidden layers and ratios of the synaptic weights, the heuristic approach to that. Okay. In fact, the hidden neurons are acting as the feature detectors ultimately, where the purpose of those feature detectors is, as I think we have already discussed, that from the input space, all right, we are, the input space is actually not linearly separable. In general it is a non-linearly separable space, but we are using the hidden layers so that at the hidden space, okay, it becomes linearly separable, and then you are applying your classification rules, okay. That is, from the original input space you are going to the space of the hidden layer activations where it is more likely to be separable, and then you are classifying it, okay. So, that is something that I wanted to talk about. So, we can accept the Bayes rule to be the decision boundary, as the optimal decision boundary. We are almost coming to the end of the discussions related to the multilayered perceptron. In fact, there are many other aspects of multilayered perceptrons that one can discuss. I think that with the amount of information which is already generated by the various research groups and people, one can spend perhaps a full semester on the multilayered perceptrons itself, but we have to restrict our discussion, we have to put a limit to it. So, I mean, we are going to put that shortly. So, in the next class, we are going to begin the next topic, which is related to the radial basis functions. But before we do that, just again one or two discussions related to the multilayered perceptron, especially about its generalization capability. So, till then